Okay, thank you for the introduction. I'm Bo Li. I'm from the University of Texas at Austin and the Hong Kong Polytechnic University. Today, I'm going to talk about file resource sharing and dorm assignment. This is joint work with Jerry Gan from the University of Oxford and Yingkai Li from Northwestern University. So before I introduce our resource sharing problem, I want to first recall you the classic resource allocation problem. In the classic setting, we have indivisible items, let's assume they are goods, and we have a set of n agents. Our task is to fairly allocate these items to the agents. Each agent I has a valuation function for all the items. So for each bundle of items, agent I has a value. This value represents how much agent I values this bundle. An allocation or an assignment of the problem is actually a partition of all the items, an n partition of the items. So each agent gets a bundle. It is assumed that no two agents share a same item. So the intersection between any two bundles of items is empty. And the union of all the items should cover all the union of all the agents bundles should cover all the items. So all the items will be allocated to agents. To capture the fairness of the problem, two very widely studied solution concepts are n-way-free allocation and proportional allocation. N-way-free allocation is stronger. It requires that for every agent I, she has a value for her own bundle that is not smaller than her value for any other agent J's bundle. So agent I doesn't want to exchange with agent J. So this is a very stable allocation. If this holds for every agent, this is a n-way-free allocation. Proportional allocation is weaker. It requires that every agent I has value for her own bundle that is not smaller than 1/n fraction over her value for all the items. So agent I doesn't care who gets what, but she only compares her value for the allocation with the threshold value. And the threshold value is just her proportional value in the allocation problem. We can see that an n-way-free allocation is also proportional. With respect to the classic allocation problem, especially when the items are not divisible, n-way-freeness and proportionality are very demanding requirements. Even when there are two agents and a single agent and a single item, an n-way-free and proportional allocation may not exist because there will always be an agent who gets nothing. The bad news is that there is even no bounded relative approximations because some agent has value 0. But the good news is that there are good approximations. With respect to n-way-freeness, people study two relaxations, n-way-free up to one item and n-way-free up to any item. The exact definition are not that important in this talk, but we know that for n-way-free up to one item, it is weaker and it is guaranteed to exist, can be easily found. N-way-free up to any item is stronger. So far, it is still unknown whether it exists or not, but for three agents with additive valuations, a recent paper shows that an n-way-free up to any item allocation exists. And there are many good approximations. With respect to proportionality, people study maximum share fairness. And we already know that it may not exist in some instances, but they are good approximations. So this is a very brief introduction about the classic fair division or resource allocation problem. What we want to study today is, what if the resource is shareable? So two agents may share a single item. For example, when we have two M students and we have M dorms, our task is to assign the students to the dorms fairly. And we know that each dorm will be assigned to two students. So these two students share an item. How can we guarantee fairness for this problem? This problem is closely related to the stable roommate problem initiated by Gill and Shapley. But in this line of research, people do not care the values for the resources or the values for the dorms. So on the other words, people assume the resources or the DOMs are homogeneous. Our question is, what if they are heterogeneous and different agents have different values for the DOMs? This problem has been studied in the market setting. And in the market setting, to guarantee the fairness, monetary transfers are needed. So the agents needs to make some payments to the mechanism designer in order to guarantee the fairness. So we know that in reality, there are many settings that monetary transfers are not allowed, especially when the problem is related to school affairs. So our problem is clear now. We want to study the setting when the agents have values for both resources and the other agents with whom they share the resource. And moreover, monetary transfers are not allowed. How can we guarantee fairness? Or to what extent fairness could be guaranteed? This is my today's plan. So first, I will formally introduce our resource sharing model and then adapt unfairness to this problem. And similar to the classic setting, we will see that unfairness is a very demanding requirement. So we relax it to Pareto unfairness, and we study to what extent Pareto unfairness can be guaranteed. And we show that for DOM assignment problem, a Pareto unfair assignment is guaranteed to exist and can be found in polynomial time. So in the last section, I will briefly discuss this algorithm. Okay, for a given resource sharing problem, we have shareable resources. And for each resource, it has a capacity, CG. So resource G can serve up to CG agents simultaneously. And in the problem, there are N agents. So in the current work, we assume the agents are unit demand. So each agent only desires a single resource, like in the DOM assignment problem, each agent requires only one DOM. And we assume the demand meets the supply. So N equals the summation of all the resources capacities. Each agent I also has a value VIG for each resource G. So this means how much agent I desires the resource G. And the agents also have external values. So for agent I, if she shares a resource with agent I prime, then her utility gain is EII prime. So this is independent with the resources. No matter which resource agent I shares with agent I prime, agent I's utility gain is EII prime. And in the current work, we assume all the external values are non-negative, but some results can be extended to the negative external values. A canonical model is required to satisfy the following three requirements. The first is all the resources have the same capacity C. And the second, the external values are binary. So it's either 0 or 1. 0 means that the two agents are not friends. If it's 1, it means the two agents they are friends. And they want to share a same resource. And third, the external values are symmetric. So for any two agents I and I prime, EII prime equals EI prime I. So if I'm your friend, you are my friend. This is if a model satisfies all these three conditions, it's called a canonical model. And an even special case is when the capacity is 2. So when C is 2, the problem is actually the DOM assignment problem. And this our major positive result is on this model. We use graphs to describe the external values of the problem. And for canonical models, this could be described as a simple graph. So in this graph, every node is an agent. And if there is an edge between two agents, I and I prime, it means I and I prime are friends with each other. So they have external value 1 with each other. And if we focus on the general model, we can just use a weighted and directed graph. With respect to feasible assignments, this is different with the classic setting. In the classic setting, an allocation is actually a partition of the items. But here, an assignment is actually a partition of the agents. So we partition the agents into M bundles and assign each bundle of agents to one resource. Because we assume no two agents, because we assume the agents are unit demand. So for every two sets of agents, the intersection is empty. And the union of all these sets of agents should cover all the agents. So every agent is assigned to some resource. Here we also have a feasibility constraint. That is, the number of agents assigned to some resource J should be no more than its capacity, Cj. And if every requirement is satisfied, this is called a feasible assignment. Next, we define the utilities. In this work, we assume the utility function is additive. So for a given feasible assignment X, the utility of every agent I is just the summation of her generic value for the resource and her external value for the other agents with whom she shares the resource. So if in assignment X, Gi is the resource that is assigned to agent I, then her utility is her value for the resource Gi plus her external values for the agents that are also assigned to resource Gi. Now we have the utility functions and we are able to define envy-free assignment. Recall that envy-freeness essentially requires that no agent wants to exchange with every other agent. So here, an assignment X is called envy-free if agent I has utility for the current allocation X that is not smaller than her utility if agent I exchanges with agent I prime. So both the resources and the roommates or the other agent should be exchanged. Here, Xi prime is the resulting assignment by exchanging the resources assigned to agents I and I prime. So both the resources and the agents are exchanged. If this holds for every pair of agents, this allocation is called envy-free. Let's see an example. So in our example, there are two resources, and the first resource has capacity 1. The second resource has capacity 2. And we have 3 agents. For simplicity, let's assume all the 3 agents have identical valuations. So all of them have value 1 for the first resource and value 0 for the second resource. And the external values are all 1. So as long as one agent shares a resource with some other agent, her utility gain is 1. We can see that in this example, every feasible allocation is envy-free. For the agent allocated to the first resource, although her external value is 0, she has value 1 for this resource. And for the other 2 agents assigned to the second resource, although they have generic value 0 for the resource, but they have external value 1 with each other. So by exchanging with any other agent, the agent's values, the utilities can't be improved. So every feasible assignment is envy-free. But we can also see that if we increase the agent's value for the first resource from 1 to some large number like 10, then envy-freeness is not guaranteed. So there is no envy-free assignment because everyone desires a lot for the first resource. And then we show that deciding whether a canonical instance admits an envy-free assignment is NP complete. So even for canonical instance, it is hard to decide whether there is an envy-free allocation or not. So this is the first result. Then we want to ask if envy-freeness has any guarantee for proportionality. Because in the classic setting, we know that envy-freeness implies proportionality. So what about when the items are shareable? Let's first define proportionality. Proportionality roughly means the average utility of each agent in the problem. So when the resources are shareable, the average value for the resources, this should be just 1 over m times each agent's value for all the resources. So for agent I, we sum up her values for all the resources and divide it by m. So this is the average generic value for the resources. What about the average external value? We just sum all the external values up for agent I and divide it by n minus 1 because we need to exclude agent I herself. And the average capacity, the average number of agents sharing a resource is C bar. C bar is the summation of all the capacities and divided by m. So this is the average capacity. Okay, now we are able to define the proportional value for agent I. It's just the summation of the average generic value and the average external values. So which is like this. But here we note that we should time C bar minus 1, multiply C bar minus 1 to the external average external values, because agent I also needs to occupy one position. And then we can define proportional assignment. That is, an assignment X is called proportional if agent I has value for the current allocation that is no smaller than her proportional value. And if this holds for every agent, this is called a proportional assignment. The bad news is that if there is some resource that has capacity 1, then an NV-free assignment does not have any guarantee for proportionality. So if we check the following example, we can see that there is an NV-free allocation, and there is one agent whose value that is arbitrarily smaller than the proportional value. So this is the bad news. But the good news is that if our resource has capacity at least 2, then any NV-free assignment ensures an approximation of the proportionality, and the approximation ratio is 1 minus 1 over C mean. C mean is the minimum capacity of all the resources. So if our resource has capacity at least 2, then this constant is at least a half. So we can see that NV-free assignment is at least a half approximation of proportionality. And this analysis is actually tight. But it can be improved if all the resources have the same capacity. That is, for the canonical instance, the approximation could be better. Okay, so this is about the NV-free assignment. We already see that NV-free is a very demanding requirement even when the items are shareable. So next, we want to relax it. Our relaxation is called Pareto NV-free assignments. So the intuition here is that we don't sum up the external values and the generic values. Instead, we treat these two kinds of values as a 2-dimensional vector, and we compare these two elements separately. So given an instance X, it is called Pareto NV-free if for every pair of agents I and I prime, at least one of the following 2 inequalities holds. So the first inequality requires that agent I doesn't envy agent I prime's resource. So here we note this is VI. VI is the generic value for the resources. It's not the utility function. So if agent I doesn't envy agent I prime's resource, then agent I doesn't Pareto envy agent I prime. If this doesn't hold, then we check the external values. So if agent I doesn't envy agent I prime's external values, this is also Pareto NV-free. So either of them holds, this allocation is called Pareto NV-free to this agent. And if this holds for every agent, this is called Pareto NV-free assignment. Then we want to study to what extent Pareto NV-freeness could be guaranteed, especially for some very commonly studied setting. The first commonly studied setting is when there are only 2 resources. We need to partition the agents into 2 bundles. And for most cases, when the resource number is 2, we see that actually there is a Pareto NV-free assignment, but not for all possible cases. And here is an example. If we check this example, we enumerate all possible assignments for this problem. We can see that there is no Pareto NV-free assignments. So we prove that. So before we prove this result, we actually want to know that for a given canonical instance, is it hard to decide whether it admits a Pareto NV-free assignment? Actually, this is the major open problem of this work. What we can show is that deciding whether a given instance admits a Pareto NV-free assignment is NP complete, even when M is 2 and the external values are binary and symmetric. But here, we note that this is not a canonical model, because in our proof, it is required that the 2 resources have different capacities. If they do have the same capacity, it is still unknown. This is about the definition of Pareto NV-freeness. And we know that it is not always guaranteed. So what we want to know is, under what conditions a Pareto NV-free assignment is guaranteed to exist. And here we show that for dumb assignment problem, there is always a Pareto NV-free assignment. Formally, we prove that For any canonical instance with capacity 2, so this is actually the DOM assignment problem, a Pareto NV-free assignment is guaranteed to exist and can be found in polynomial time. In the following, due to time limit, I'm not able to give you the details about the algorithm, but I want to show you some intuition. Let's first recall the definition of Pareto NV-freeness. It requires that for every pair of agents, I and I prime, either agent I doesn't envy agent I prime's resource, or agent I doesn't envy agent I prime's roommate. Because the capacity here is 2, so there is only one roommate. Given this definition, we can have a very simple observation. That is, given 2 agents, I prime and I double prime, if both of them are not agent as friends, then let's assign one DOM to these 2 agents, I prime and I double prime. No matter which DOM is assigned to them, we know that agent I will not Pareto envy them, because agent I is not, because both of them are not agent as friend. So by exchanging with one of them, agent I's external value can't be improved. This observation is quite straightforward, but it plays an important role in our algorithm. Given this observation, we have a sufficient condition for Pareto NV-freeness. To guarantee Pareto NV-freeness, it suffices to guarantee the following for each agent I. Either agent I obtains a better DOM than all her friends. If this condition holds, it means that agent I will not Pareto envy her friends because her resource is better than them. Moreover, by the above observation, we know that agent I will not envy Pareto envy non-friends. Because they are friends and no matter which DOM is assigned to them, agent I doesn't Pareto envy them. If this condition doesn't hold, we check the following. Or agent I shares an arbitrary DOM with one of her friends. So as long as agent I shares a resource with a friend, her external value is 1. This is the maximum he can get from the external value. So agent I will never Pareto envy any other agent. Okay, so in the following, we design an algorithm such that for each agent, one of these 2 conditions holds. The idea is like this. We first compute a maximum matching in the externality graph. And if this maximum matching covers all the agents, then we are free to assign each pair of agents, matched agents, to an arbitrary DOM, so that the second requirement is satisfied because everyone is sharing a resource with a friend. So this is the ideal case. The tricky case is if this maximum matching can't cover all the agents. What shall we do for the uncovered agents? So by above observations, we know that we want to guarantee that for these uncovered agents, we want to assign each of them to a better DOM than all her friends. This is not easy to guarantee because the agents have arbitrary preferences. So our key techniques for our algorithm include the following 2. One is the Gala-Edmonds decomposition, and the second is Hall's theorem. So let's first recall these 2 theorems. For Gala-Edmonds decomposition, so given an externality graph, given any simple graph, G, let A be an arbitrary set of nodes. Let's remove these nodes. Let's remove A from the current graph. Then there will be several connected components in the remaining graph. We use B to represent the set of all even connected components. So for each component in B, it contains even number of nodes, even number of agents. And we use D to represent the set of odd connected components. So for each component in D, it contains odd number of agents, odd number of nodes. Then the set A is called a TAT set. If the following holds, if for every possible maximum matching M of the original graph G, it can be decomposed as the following 3 parts, MB, MD, and MAD. Here, MB is the set of perfect matchings for all the even components in B. We know that for each component in B, it contains even number of nodes, and there should be a perfect matching for each even component. and MB is the union of all such perfect matchings. For each component in D, it contains odd number of nodes. So there is no perfect matching, but there should be a nearly perfect matching. So it covers all but one agent. And MD is the union of all such nearly perfect matchings. So far, we know that all the agents in even components are covered. And for every odd component, it covers all but one agent. And then we have matching MAD. It is a matching between A and the uncovered agents in D. And this matching should match all the nodes in A. So every node in A is matched to a node in D. And we know that for all possible uncovered nodes, they should be in some of the odd components. So if every maximum matching can be decomposed like this, A is called a TAT set. So this is a very strong decomposition. And by the following lemma, we know that a Gala-Edmonds decomposition exists and can be found in polynomial time. Let's see an illustration. So in this graph, for simplicity, we assume the TAT set A only contains one node. And let's remove this node from the graph. There are some remaining connected components. All the even components are in B, and all the odd components are in D. For all the even components, they contain perfect matchings. And for odd components, they contain nearly perfect matchings. And the nodes in A should be matched to these uncovered nodes in the odd components by the nearly perfect matching. And all the nodes in A should be covered, should be matched. This is called Gala-Edmonds decomposition. I believe most listeners will be familiar with Hall's theorem. So given any graph G and any set of nodes S, we use NS to represent the S neighbors, the neighbors of S. And Hall's theorem says that for any bipartite graph with two sets of nodes L and R, L can be fully matched if and only if for any subset S of L, the sets of S should be no more than the sets of their neighbors. So if this holds for every possible subset of L, then L can be fully matched. This is a necessary and sufficient condition. Now we are able to briefly describe our algorithm. Given any instance with the corresponding externality graph G, so we first decompose the externality graph. So we compute the Gala-Edmonds decomposition ABD of G and one corresponding maximum matching M. And M is decomposed according to the Gala-Edmonds decomposition. And here is an illustration. So in this graph, the set of even components is on the left, and the set of odd components is on the right. In the middle, A contains the TAT nodes. And all the solid lines represent the maximum matching, the current maximum matching. Next, we will try to assign the agents to some DOMs separately according to which component it belongs to. Let's first deal with the agents in the even components. We know that there is a perfect matching, and all these nodes are covered by MB. What we do is that we arbitrarily assign each pair of matched agents to some available DOM. So we find one arbitrary one available DOM for each pair of agents in B. After this step, we know that the agents in D will never Pareto N with them. We will never Pareto N with the agents in B because they are not connected. If we remove A from the graph, they are in different connected components, so they are not friends with each other. Agents in D in the odd component will never envy the agents in B. Okay, this is okay. But we know that agents in the TAT set A, they may be connected with the agents in the even components. So A may Pareto, potentially they may Pareto envy agents in B. So in the following, if we want to make sure this step to be valid, we need to guarantee that all the agents in A will be accommodated to some dorms with their friends. Let's recall that this is the second condition. If this holds, this is also unfree to the agents in the TOT set. So we need to keep this in mind in the following procedures. Next, we deal with the agents in the out components. We know that there is no perfect matching. For each out component, let's suppose the studied component is DI. There is a nearly perfect matching. It covers all but one agent in DI. So let's assume I is the agent that is not covered by this matching. Then what we do is that we ask agent I to select DOMs from all available DOMs to these for these paired agents. That is, agent I selects her least preferred DI-1 over 2 DOMs because they are only DI-1 agents. And for each pair of matched agent, one of these DOMs is assigned to them. After this step, we know that all the agents in the other out components, they will not Pareto envy these agents because they are not connected. And agent I will not envy them because agent I selects her least preferred DOMs for them. So this is also okay. And agents in the even components in B, they will not Pareto envy them because they are not connected, and agents in B already have a friend in their room. Again, the problem is for the agents in the TOT set A. A may be connected to these agents. Each agent in the TOT set may connect it to multiple nodes in a single out component. So in the following, to guarantee this algorithm to be valid, that we need to make sure that A will be accommodated with her friends to some DOMs. This is what we do with the out components. Okay, so far we have accommodated agents in the even components and the agents in the out component, and also covered by the nearly perfect matchings. We already assign them to some DOMs. So the only unassigned agents are all agents in A, and for each out component, there is one uncovered agent, unassigned agent, and we use L to represent all such agents. So there will be a resulting bipartite graph between A and L. So we need to note that for each out component, there is only one node. There is exactly one node in this set L. And there is a perfect matching between A and L. What we want to do that we need to guarantee that all agents in A should be accommodated to some rooms with their friends, and all agents in L either they are assigned to some rooms that is better than her friends, or they are accommodated with their friends. Our first attempt is to use the current maximum matching, but it is very hard because the agents have arbitrary preferences. We can't guarantee these requirements for every agent. So what we do is like this. I don't have enough time for this part, but the intuition is like this. We don't use the current maximum matching. Instead, we repeatedly find a subset of agents in A and properly match them to some nodes in L, and properly assign this subset of pairs of agents to some DOMs, so that after this assignment, all the remaining agents in A could still be perfectly matched to L, matched to the remaining nodes in L. And for all the remaining nodes in L, either they can be accommodated with friends, or they can be assigned to some DOMs that are better than all her friends. And this is basically guaranteed by Hall's theorem. And until there is a perfect matching between A and L, if so, this is the simple case. We can just assign them to some arbitrary DOMs because everyone is sharing a DOM with her friend. If you have interest, maybe we can discuss this part later. Okay, next, I want to mention that Our above algorithm is valid for binary external values. So either the external value is 0 or is 1. And this can be easily extended to the case of non-positive external values. So it's either 0 or -1. So if they are friends or they are indifferent with each other. But maybe an interesting future direction is to study trinary values. So for every pair of agents, either the external value is -1, or no, it's either -1 or 0 or 1. So either they may be friends, they may be enemies, or they may be indifferent with each other. This is the first future direction. The second open problem is this work is, as I have mentioned, we still do not know whether it is NP hard to compute, to decide whether a given canonical instance admits a Pareto free assignment. And the third direction may be to study the proportionality. Actually, in this work, we have briefly discussed the proportionality and Pareto proportionality, but a systematic study of proportionality is still missing in this work. So maybe it is interesting to study this part. This contains all that I want to mention today. So in conclusion, in this work, we propose the file resource sharing problem and then adapt NV freeness to our model. And we relax the NV freeness to Pareto NV freeness. We study to what extent a Pareto NV free assignment is guaranteed to exist and how to find them. Particularly for DOM assignment problem, we design an algorithm to find a Pareto NV free assignment. And if the capacity is increased from 2 to 3, then a Pareto NV free assignment may not be guaranteed anymore. Okay, thank you. Thank you very much. Welcome for questions.
Okay, thanks both for the nice talk. So I got some questions from the audience. So can you hear me clearly?
Yeah, I can hear.
Sorry. Okay, cool. So yeah, actually there's a question in this Zoom room. So let me read it. Why in canonical model the external value is only allowed to be 0,1 but not 0C, where C is a positive number?
Actually, it is okay because for Pareto NV freeness, we compare the generic values and the external values separately. So you are free to assign the binary values are either 0 or some other constant C. It doesn't need to be 1.
Okay, great. So the second question is that, can your result generalize to general external utilities? What may be the hardness of general external utilities?
You can see that the major component of our algorithm is the Gala-Edmond decomposition, and it only holds for simple graphs. If the external values are arbitrary, so far we still do not know how to decompose the graph and study the corresponding external values. So I think this is the major difficulty.
Okay, so there's another question. Well, so you mentioned C equals to 2. So what about C equals to 3? Is there any similar results, or will be NP complete?
When the capacities are all 3, we have some examples that there is no Pareto NV free assignment. But our proof is for very large capacity. So I'm still not clear whether for capacity 3 it is NP complete or not. Sorry.
Okay. Thanks. I think I don't see any further questions. So let's thank the speaker again. And that concludes Bolly's talk. Thank you.
Thank you very much for your time.